Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to continue to talk about bearing strength, and we're going to talk about all of the different parameters that are inside the bearing strength equations, because there are some tricks to them and some background as to why they exist. So if we recall what our compression perpendicular to grain resistances are, we had two: the effect of all applied loads and the effect of loads applied near a support. In the previous video we talked about how we can tell where I need to do which check A or check B. But in this video, we're going to talk about how do we calculate bearing area, how do we calculate the length of bearing factor KB, and how do we calculate the size effect factor. Sorry, this KB should be capital B. How do we calculate the size effect factor KZCP? Okay, and then likewise, when we get down here to effective loads applied near a support, we have an average bearing area, because we can have bearing on the top and bottom of a beam, for example, that are within D of the support from each other. So how do we calculate that bearing area? So first, we're going to talk about how do I calculate the bearing area. So I'm going to draw a couple diagrams so that we can discuss exactly what kind of thing that looks like. Okay, I mean, these pieces of wood are pretty warped, so I guess they came from the bargain bin at Home Depot, but let's talk about the bearing area. So on the left side, one thing is basically wherever the contact is. So let's say that I had a steel plate, for example, that was sitting on top of this member. Okay, then where that steel plate was in contact with the wood, that would be the bearing area. So if I had something that looked like this, right, then this area is the bearing area. Okay, so it's covering some subset of the top of the plate, and there are loads that are pressing down on that, obviously. But this area in here is the bearing area AB. I mean, maybe more common is, I have two pieces that are overlapping, and the bearing area in this case on the right, where I have, for example, a joist sitting on a beam, is whatever is the overlapping area between the two where they intersect. So, in this case, if the beam is, 80 wide and the joist is 38 wide, then I have 38 in this dimension, and I would have 80 in this dimension. So it would be 38 times 80 would be my bearing area. So here is my bearing area, AP. Okay, and if I were to number these joists, or these beams, if this was number 1 and this one was number 2, then this bearing area would apply to both compression perpendicular checks on number 1 and number 2. Because remember, I have to check what is the bearing strength of the beam in resisting number 2, and in turn, what is the bearing strength of number 2 resisting the reaction load from the beam. So, but those two areas for those two calculations would be the same, but the strengths might be different because they might be different materials. Okay, so that's pretty simple. That's just what bearing area is in general. What about if I'm calculating my QR prime, which is my squeezing load, and then I need an average bearing area? What does that look like? So let's say I have a beam and I'm looking here at an elevation on the left and a cross section on the right. So this is the same beam. And I have two bearing plates, one on the top, which has a length LB2, and that length LB2 is in the longitudinal direction of the beam. And it has a width of B1, which I can see on the right, which is in the perpendicular to grain direction of the beam. And I have another plate on the bottom, which is a different size, which has a smaller length, LB1, on the bottom, and a width of B2 on the right. And these two plates are within D of each other along the beam. So they're close enough that I have to consider the squeezing effect, which is the effect of loads applied near a support, so-called near a support. So in this case, I have to calculate the average bearing area AB prime for this equation, QR prime, which is the squeezing. I call the squeezing equation. Okay, so first I calculate the average bearing width, which is very easy. It's just a straight up average. B, which is the average bearing width, is just B1 plus B2 over 2, which is just literally the average of those two numbers. So this is the average bearing width. And then once I have that average bearing width, I calculate an average bearing area, AB prime, which is B, the average bearing width, multiplied by, unsurprisingly, the average bearing length. And you might ask, why are we doing this? Why don't we just calculate the area of the top one and the area of the bottom one and find an average of the two? It's because they have this extra requirement that the average bearing area has to be less than 1.5 times the bearing area of the shorter plate. So the shorter plate in this one is the bottom. It's not really the area of that plate. It's the area of the it's the length of that plate times the average bearing width. So this is a requirement that keeps you from compensating for a very short plate by putting just a really long plate on top. Obviously that doesn't make sense because the short plate will still be applying a really high concentrated load over a very small area, which means that we're probably going to end up having a local effect that exceeds the 1 millimeter requirement for compression perpendicular. So this is to keep you from doing any funny business. So caps the average bearing area to 1.5 times the smaller bearing area, approximately 1.5 times the average width times the smaller bearing length. Okay, so that's all that you really need to know about calculating bearing area. Next, we're going to talk about length of bearing factor, and this one is particularly interesting. So just like everything for bearing effects, it's basically identical for lumber and glulam. So if you design a lumber beam, you go to these clauses and this table for calculating length of bearing factor. And in the glulam section, it just refers back to these exact same tables in chapter 6. So let's look at what this effect is. Okay, so we've seen something similar like this before. When we push down on a piece of wood that's going to bear into another piece of wood, or not, it doesn't have to be a piece of wood pushing down, could be anything, could be a piece of steel. And we push down on the surface, we are compressing the fibers, but we're also deflecting them downwards. So the fibers on top of squishing also kind of have a deflection, which it means they kind of bend down like this, which is what I'm trying to show here. These here in orange, I'm showing the fibers. So since those fibers are continuous running underneath that piece of wood that's bending them down, they actually, although they do get squished, when they deflect downwards, they also get engaged in tension. So you can think like if my elbows were locked in place and I push down here, the further I push, the more I'm engaging these fibers in tension, right? Especially if I have fairly large displacements, I'm going to get tension in these fibers. And that means that I have some resistance to pushing down, just like if I had a guitar string and I try to push it down. When I push down on it, it increases the tension in the string, and that provides resistance to me pushing. So this provides actually an additional mechanism of strength to the compression perpendicular resistance, but it depends on the relative geometry, as we're going to show. So I like to call this the trampoline effect, and I'm going to show exactly what I mean. Okay, so here I'm showing the difference between a short bearing length on the left and a long bearing length on the right. So we're looking at the surface of a piece of wood, the side surface. So here, and we're pushing down either with a short bearing or with a long bearing. And we remember from before that our criteria for failure here is that we, when we get to 1 millimeter, we consider that we have compressed the surface enough and we don't want to compress it anymore. So we set our strength equal to the stress in the surface when that 1 millimeter is reached. But as we're bending down, so we have the strength of the fibers in squishing, like this causes, this requires some force to squish the fibers like that. But in addition to that, we have this effect of the trampolining, where as I bend these fibers down, there is some resistance because I am engaging them in tension, like as if I was pushing down on a trampoline or on a guitar string. So we have the same thing happening for both long bearing and for short bearing. We get the same kind of effect. And this effect will be largely based on geometry. So I'm just going to draw now kind of a free body diagram somewhat of the surface. Okay, so you can imagine now, just without considering this trampolining effect, if I was just looking at crushing, I have two forces. I have an applied force coming down that's pushing the surface, and at the bottom I have a force that's resisting that push, which is my what I've referred to here as WL short. Okay, so that's basically the distributed load W times the short length, and that can only go as high as the bearing capacity. So as I increase the force coming down, I accordingly increase the force on the bottom, right, which is resisting it, which is the squishing resistance, just this effect. Okay, I have the same thing on the long. The only difference is that the surface is longer. Now let's say I add in that effect, the trampoline effect, where I have effectively a force acting on an angle that's trying to pull it back up, right? So this is just following the line of basically the edge of the surface as it deforms. And let's say I give that some value, and I have it on both sides. I have it here as well. Same force, same kind of force, right? Now, what if I look at what is the horizontal, or what's the vertical, sorry, the vertical component of that angled force, and let's call that P. Okay, so I can do that same thing here, and I can have P. Okay, so P is the vertical component of that force on an angle, that trampoline effect force. Now, when I finish my free body diagram and I determine what's the load applied on the top now, I find, right, that this on the top here is WL short, right, plus 2P, right? And here I have WL long, doesn't read very well, long, plus 2P, okay? Same on both sides. Now, we know that the displacement is the same. It's 1 millimeter. So I think we can also assume that these P forces are about similar as well. And they can be significant, but I think it's clear here that since on the short side, the WL is a smaller portion, the P will have a bigger relative effect for a shorter bearing section than a longer bearing section, which will have a smaller relative effect of P. So for the long bearing surface, this P might be a force that is very small relative to what is the total contribution of just the squishing part, the WL long. So 2P is quite a bit smaller than WL long, but as I get shorter and shorter, that trampoline force becomes more and more of a percentage of the total resistance. And, you know, if it was 50% of the total resistance, then that would mean that I could basically take double the force for the short bearing capacity than I could for a very long one, right? So if on the left, 2P and WL short were the same value, then I'm basically doubling my resistance, right, by taking into account this trampolining effect. And we can see that the value is actually pretty large if we look at the table, which I intend to do right now. Okay, so here's the table for KB, and we can see that as the bearing length decreases, as we go up, the modification factor KB becomes larger. So I can actually take a lot more force on a small bearing area, like we said, than I can on a large bearing area. And you can see that the effect tops out at 150. At something 150 or longer, that effect, that trampoline effect, becomes so small as to basically become negligible and not worth considering anymore. But for very small ones, you can see I get almost twice the strength for 12.5 millimeter bearing length or less, which is very, very significant. So it's important to take this into account when we can, but there are some times when we actually are not permitted to take this into account. So let's look at those. So I'm just going to put a couple more notes here. Okay, so just like we said, the shorter the bearing length, the higher the KB, and once the bearing length gets greater than 150 millimeters, then KB saturates basically at 1.0. We can't have a less than 1.0 KB because we're at KB 1.0, it just means that the bearing effect is negligible. Okay, and we get that KB from the table that I just showed you, which is table 6.5.7.5. Okay, so there are some restrictions to when we can consider KB, because this trampoline effect cannot always be present depending on some other considerations. So let me show you the first one. I'm going to draw it and then we'll talk about it. Okay, so the first one is that no part of the bearing area can be within 75 millimeters of a member end. If the bearing area gets too close to the member end, what's basically happening is I don't have a trampoline anymore, because for the trampoline effect, I need both my elbows, for example, to be restrained, right? So that when I push down, I can pull against those supports, right? If one side is not restrained and I bend it down, it just drops, right? There's no restraint. There's nothing causing those fibers to engage in tension anymore. So then I can't consider this, this KB effect. So the reason is because no trampoline with support on only one side. We can't imagine a trampoline that has a support on only one side. Right? It would look like this. Right? And so I couldn't take any tension force here. Okay, the other requirement for being able to apply KB from that table up to 1.75 is that the bearing area is not in a region of high bending stress for the member that we're bearing on. So in this case, we have a beam, for example, and that beam has some bending moment in it from whatever loads are being applied. And if this is an area of high bending stress, you know, I'm showing a stress distribution on the left. So this is all stress. Okay, so we have compression in the bottom, tension in the top. There's two things that can happen. The first thing is, if it's tension in the top and the tension is really high, then that means that the fibers at the top of surface are already in a really high, they already have high axial stress in those fibers. They already have high tension. So then we can't rely on those fibers to take additional tension caused by the trampoline effect. For the side that's in high compression, basically that means like if the fibers are all bunched up and they're in high compression, then I may not be able to actually engage the fibers in tension at all. They may be in compression that entire time. So again, I won't be, if I'm not engaging the fibers in tension, I can't have that trampoline effect. So both sides don't work. That's what I just said. On the tension side, it eats up some of the available capacity, so we can't resist the bearing. And on the compression side, the fibers are prevented from engaging in tension altogether. So if I don't satisfy both these requirements, the requirement that I'm not within 75 millimeters of the member end and I'm not in an area of high bending stress, if I don't satisfy both those requirements, then KB equals 1.0. This basically means that I cannot include the effect of KB, the bearing factor, the bearing effect factor. How do I know whether it's an area of high bending stress is not defined. So that is up to you as an engineer to reasonably determine whether that area is in a high bending stress or not. I mean, if you're talking about a bending beam and it's the center of the beam, and that beam is designed, basically the resistance is designed for bending and not from some other consideration, then certainly that would be one situation where you're in an area of high bending stress. If your beam is designed for deflection and you have maybe some considerable strength left over, then maybe it's not, but probably you would still err on the side of caution and not include it. So if your bearing is towards the end of the beam, and it's in an area of high shear but not high bending, then that would be a good time to consider KB. Maybe the center third of a beam that's in simple support might not be the best case to consider this. But again, it's up to your discretion about whether to consider that or not. So the very last factor that we need to consider in the equation for compression perpendicular resistance in O86 is the size effect factor. So this is one of those situations where size effect factor for this particular resistance is not directly related to grading, but instead it is related to grain orientation. Of course, grain orientation is one portion of grading, but that's in terms of tension strength, for example. Grain orientation is an important component to grading, but this is something that's not generally graded for compression perpendicular. So what they do is basically everything is calibrated for compression resistance, compression perpendicular resistance, to the worst case scenario for bearing. And the worst case scenario for bearing happens to be when the grain is at a 45-degree angle to the bearing. So something that looks like this. So if I have bearing on the top and this grain, I mean, obviously these are radial lines, so they're a bit curved. But if this is approximately 45 degrees, then that's the worst case. And since we don't know the grain orientation in our piece of wood, then we can't really predict what our orientation is going to be. But there is a special case. So if our piece of wood is oriented like this, then I mean you can see on this one that I have that we're pretty close to 45 degrees. Okay, if I'm on this side, for example, if I'm bearing on this side, I'm pretty close to 45 degrees. If I flip it the other way, maybe I'm not close to 45 degrees anymore because the grains they've turned to become more vertical. Now, if I lay the piece on its side, then actually part of the bearing surface is likely not to be at 45 degrees. So you see here about half of the bearing surface is at a 45-degree angle. But by the time we get over to this side, it has rotated around so that now I have kind of part of my bearing surface is now at a flat angle, right? Which was not the case here. Here it was basically all or nothing because the side is so short relative to the grain that basically If one side has 45 degrees, the whole thing is 45 degrees. But if I flip it on its flat, then not the whole thing is going to be at 45 degrees. Part of it is not going to be. And so this is basically this size effect factor accounts for this. So for example here, now that I've drawn one out kind of on the flat, it's much more likely that only a portion of it is going to be loaded in the worst case. So for example here, maybe this portion and this portion are 45 degrees, but the center is not. So maybe that means that I can increase my strength a little bit. And it's not a huge bump. And basically you get the values from this table. Okay, table 6.5.7.4. We can see here that if the ratio of member width to depth is 1 or less, which means basically you have a vertical piece like this because width here is small, depth is big, therefore it's always going to be less than 1, then KZCP is 1.0. If it's 2 or more, like this one is, right? So this is width divided by depth is 2.0 or more, then I get to bump it by a little bit. KZCP goes, I increase my strength by about 15%, which is pretty good bonus. And if I have something in between, then I can interpolate. I'm just going to write this into the note. This is basically the same as what the table says. If the width over depth is greater than 2, then I can bump up my strength to account for this effect. If it's less than 1, then I cannot add anything to my strength. There is one more caveat to this, which has to do with glue lim. Okay, so if I have glue lam, we know that it looks like stacked pieces of lumber, like this, for example. That's a glue lam cross section. So if I'm pushing on the top of this, I'm not pushing, it's not like, even though this member, the aspect ratio of this overall member is tall, right? It's not the same as loading like this. Why? Because here I'm loading on the short end of one piece, right? I'm loading on the short end of one piece. But in this case, for the glue lam, I'm loading actually on the long side of one lamination. So obviously the grain direction is related to this piece, the geometry of this piece, not the geometry of the entire section. So when I do width versus depth here, it's this width times this depth, which is the depth of one lamination. That's usually, if you want to assume something for calculation, you can assume 38 millimeters, which is the same size as this. And that takes us to the end of the explanation of design for bearing. And next we're going to get into a full example of how to actually do these calculations.